Today we are going to discuss Lorentz transforms, which govern how distances and times are measured in different reference frames moving at different velocities. Lorentz transforms were first derived by Albert Einstein as a symmetry of the Maxwell equations in his special theory of relativity, but have since seen wide applicability in many areas of physics. Lorentz transforms can ultimately be derived from the idea that any two events in spacetime, A and B, have an invariant interval between them. Now, let's take a closer look at what this invariant interval actually means. So, suppose we've got two events, A and B, with A at the origin. So I can write that the position of A is equal to 0, 0, which is at position B equals delta t and delta x. So we can compute the distances between these two events, and special relativity tells us that the distance, delta s squared, is given here by c, the speed of light, times delta t squared minus delta x squared. Now let's suppose we've rotated into a different coordinate system, where x becomes x prime and t becomes t prime. Now the position of A has not changed in this so-called primed frame, so we can still say that its position is at the origin, 0, 0. But clearly the position of B in this new set of coordinates has changed. So we can write that position as delta t prime, comma, delta x prime. And as before, we can compute the distance. Delta s prime squared, distance is measured in the prime frame, is equal to c delta t prime squared minus delta x prime squared. Now, one thing to note from our diagram at the left is that despite the change of coordinates, the distance between event A and event B has not changed. Similarly to how in normal 3D Euclidean space, if you're shifting between Cartesian and cylindrical and spherical coordinates, you can just put different labels on the coordinates, but the distances between points fundamentally do not change, equal to delta s prime, the spacetime interval as measured in some other frame. And this is why the interval is considered invariant. And this invariance forms the basis of the Lorentz transformations. So we can make this concept of invariant intervals a little bit less abstract and deal with actual physical situations. Now, the two important ones to describing Lorentz transforms are time dilation and length contraction. So let's go back to our 2 points, point A, and then we can have point B over here. But now we're just plotting them in space. We're not plotting them in space and time. So let's say I've got an object. Here's the velocity v. So we can analyze these events from the point of view of an observer who's apparently stationary relative to points A and B in space. And this is what is known as the lab frame. We can write the spacetime interval, or the invariant interval between these two events. That's delta s squared equals c delta t squared minus delta x squared. We can also analyze these events in the so-called rest frame, where we're effectively sitting on top of the particle and the apparent velocity we measure is 0. We can find another delta s prime equals c delta t prime minus delta x prime. But since we're effectively sitting on top of the particle, we're not really moving with respect to it, so any delta x prime in the particle frame will drop out. So now we can recall that the space-time interval is actually an invariant quantity. So as we derived before, delta s squared equals delta s prime. So this implies that c delta t squared minus delta x squared, both of these as measured in the lab frame of a stationary observer, equals c delta t prime squared, where t prime is the amount of time that's passed between the object being at point A and the object reaching point B from the point of view of someone who's sitting on top of our moving particle. Now, one of the things we can do now is divide both sides through by delta t. We can factor out the c squared and divide it through. Now, what is delta x over delta t? That is simply the velocity of our particle. So we can simplify this further. And then finally, we can take the square root of both sides. So this is the essence of time dilation. So the faster an object is moving, the slower time appears to pass for it. And we can denote this time dilation factor delta t prime over delta t as equal to gamma to the minus 1. One other physical situation we can analyze with invariant intervals is known as length contraction. So to study this, let's look at a slightly different physical situation where we've got a rod of length delta x. And let's consider two events. As before, A, when the front or the right-hand side of the rod crosses a certain point. Event B, denote where the left-hand side of the rod crosses a point. Now in the rest frame, where does the right-hand side of the rod cross some point? It'll be at the right-hand side of the rod. Where does the left-hand side cross that given point? It'll be at the left-hand side of the rod. We can draw some sort of a finish line over here. But these events take place when the right-hand side and the left-hand side of the rod cross it. Now we can analyze the situation in the rest frame of the object and construct an invariant interval. So in the rest frame, delta s squared is going to equal c times delta t as measured in the rest frame squared minus delta x squared. And the reason we're saying delta x and not some delta x prime is because the distance we are measuring from A to B is delta x, is the distance between the left-hand side and the right-hand side of the rod. If we're sitting on top of the rod, nothing will change about the length of the rod, as viewed from that perspective. We can also study this event in the lab frame of some stationary observer. We can also study these two events in the lab frame of some stationary observer. Now in the lab frame, there's no spatial separation between these two events because event A and event B lie on the same finish line, which is stationary in our frame. So we can write, in this case, delta s prime squared equals c delta t prime squared minus delta x prime squared, which will disappear as before. So now delta s squared equals delta s prime squared c delta t squared minus delta x squared equals c delta t prime squared. So now we can depart slightly from what we did earlier, and we can make the substitutions that delta t equals delta x, the length of the rod as measured in the frame co-moving with it, divided by the velocity. And that delta t prime equals delta x prime, the length as measured in the lab frame, divided by the same velocity, since the two frames have the same magnitude of relative velocity. Equals c squared over v squared delta x prime all squared. Then we can make a further simplification equals delta x prime squared. And take the square root of both sides. We will get that delta x prime divided by delta x is equal to 1 minus v squared c squared to the 1/2, which is equal to that factor we mentioned, gamma to the -1. Having derived all these tools, we're now in a position to be able to assemble them and derive the Lorentz transforms. So the way we're going to do that is to suppose we've got an observer in the lab frame, which we've got an object that starts out at a position delta x. Let's now say that this object is moving at a velocity v. So in the lab frame, we would get the position delta x sub lab equals v delta t lab plus the original displacement. But since we're moving at a velocity, any sort of distance in the rest frame will have to be contracted by that factor gamma when we're transforming back into the lab frame. So you can get delta x lab minus v delta t lab times gamma is equal to delta x in the rest frame. Now we can flip this around from lab frame to rest frame, recognizing the fact that if we have an object that's moving at v in the lab frame, that means that the observer in the lab frame will be moving at minus v with respect to the rest frame. So these are the two Lorentz transformations for distance. Now we can combine these together and we can compute Lorentz transformations in time as well. So I'm not going to work through the algebra over here, but if we were to work through it, we would find that. So these are the Lorentz transforms. One thing in particular to note is that distant transforms only work with the x component that's parallel to the velocity v. So for example, if you're looking at a train car that were proceeding directly away from you, the width and the height of the train car would not appear to transform because the width and the height, the directions in which they point, are perpendicular to the velocity of the train. One practical application of the concepts behind Lorentz transforms is deriving a relativistic generalization of the Larmor formula. To start with, let's consider in the lab frame a particle moving at velocity v and an acceleration a, and a and v need not necessarily be parallel. We can decompose the acceleration into a equals a parallel, the component parallel to the velocity, plus a perpendicular, which will be perpendicular to the velocity. Now a parallel equals, whereas a perpendicular, from length contraction, we know that x parallel in the lab frame is about gamma to the -1 x parallel in the rest frame of the object. And we also know via time dilation, t in the lab frame is about gamma times t prime in the rest frame. We can find that a parallel is proportional to gamma to the -3 a parallel prime in the rest frame of the object, because we have one factor of dx parallel over here and two factors of dt parallel on the bottom. We can do a similar thing for the perpendicular case, but length contraction does not apply because we're in the perpendicular direction, so that just gives us a factor of 1. But time dilation still does apply, so we collect a factor of gamma in dt for that. We have two factors of dt, but no factor of gamma at the top. A perpendicular is about gamma to the -2 a perpendicular prime. Now in the rest frame, we're moving at zero velocity, which is the situation for which the Larmor formula was derived. So we can just compute the power as P equals 2/3 q squared times a parallel squared plus a perpendicular squared. Just breaking up a squared into parallel and perpendicular components, as we can do with any vector. And these are primed because they're measured in the rest frame. And this equals 2/3 q squared over c cubed, gamma to the 6 a parallel squared plus gamma to the 4 a perpendicular squared. This is exactly the formula that you would get from a more complicated derivation, just done with dimensional analysis. Thanks for watching this video. I hope you enjoyed it, and I hope that it was informative.